we are online, and I think we're starting the recording, and we can wait a few minutes for people to to join. I see they're already coming in. Let's wait a few minutes, and then we start. Okay, let's wait until 1 minute past 4. Okay, there are still lots of people coming. Very good.
Are you based in Durban at the moment?
Yes, I'm based in Durban at the moment. Yeah, no, thank you very much. Yeah. Okay, let's. We have a few seconds to 1 minute, and then we can start. Yeah.
Shall I share my screen?
Yeah, you're welcome. Yeah, you're welcome. And so people can look at your first slide while I'll introduce. And maybe while you share the screen, I can start to introduce you. Yeah. So good afternoon, everyone. Welcome to this edition of the colloquium of NITheP. And this afternoon, we are very fortunate to have Professor Gerard Milburn with us. Gerard is speaking to us from Australia, so it's a little bit deep in the middle of the night for him. So thank you very much for that, Gerard. I highly appreciate it. So Gerard is famous for his work in open quantum systems, quantum optics, quantum measurement, control, and the list goes on, optomechanics, and so on and so forth. And he has written some of the best textbooks on quantum optics, quantum measurement, and control. And more recently, a book on optomechanics that are all highly recommendable. And but also he also written a few popular books that are really fantastic. And one of them, I don't remember in which edition, is called Schrödinger Machines, yeah, which is a really fantastic introduction to quantum computing and other similar technologies. Yeah. But many of you might know Gerard because he proposed long ago in a pioneering paper a way to build quantum computers with linear optics, which has played a very crucial role in the development of quantum mechanics. But today he will speak about a slightly different topic, which is probably interesting to lots of us or lots of the participants here, which is some maybe non-conventional aspects of machine learning and relationships to thermodynamics. Yeah, but I don't want to spoil the topic of the talk. So Gerald, thank you very much for being with us. You're welcome to start the presentation, but Ilya, yeah, sorry, I see that
we see the black screen, and also
yeah.
I see the black screen, and some participants also write in the black screen.
Yeah, I think you might be in the wrong window. At the beginning it was there, but then something happened. Yeah.
Probably I went to full screen. Sometimes that doesn't work properly.
Yeah, no, I know. Yeah. Yeah, okay.
Is that working?
Yes, now we are in business. Thank you very much. Yeah.
Okay.
So Gerald, please, it's your show, not mine. Please, thank you very much.
Okay. Very good. Thank you, Francesco. It's great to have this opportunity to speak to you all. This is something of a new subject for me, and I've learned a lot from your work and your colleagues on machine learning in South Africa. So let me first of all thank my collaborators, Sally Shrapnel, who was a former PhD student of mine, curiously enough in philosophy rather than physics, although she's appointed to physics these days, and is my go-to person on machine learning. She got me interested in this subject a couple of years ago. And Michael Cuming was a former PhD student I co-supervised, who has also participated in this project. Part of the talk is about clocks, which may seem a little paradoxical in the context of machine learning, but I hope it will become clear. And that work has been funded by FQXI, the Foundational Quantum Institute. And of course, all of this work was conducted in the Australian Research Council Centre for Engineered Quantum Systems. Okay, so let me begin. Press the right button now. So here's an outline of the talk. I'm going to talk about the thermodynamics of clocks with a particular emphasis on quantum clocks and the role of continuous measurement in defining these things. Then move on to the thermodynamics of machine learning and clocks. And some of you may anticipate the connection in terms of spiking, what's called neural spiking as a way of doing machine learning. And then I'll finish with some comments and conclusions. Okay, so the first thing I want to note is that all clocks, classical and quantum, are irreversible systems, necessarily so in order to remain stable. They are pushed away from equilibrium by typically some external system doing work on them, some continuous driving. And this departure from thermal equilibrium is measured by a positive change in the free energy of the clock, which has two components, one coming from the work done, delta E, and one coming from the change in entropy. I'll be mostly concerned with clocks driven by work in this talk, but you can also drive clocks by reducing the entropy through measurement, but I won't have a lot to say about that in this talk. So if you do work, you can increase the free energy. And I've written a review of this recently, which is published in this fairly generalist journal for reviews called Contemporary Physics. Okay, so here's a typical clock. It's a pendulum clock. The work done is done by gravity due to a falling weight. And it has a pendulum, which is the primary oscillator. And that's coupled in a highly non-linear way to what's sometimes called the anchor and wheel or escapement mechanism. And this is a key part of the clock. This is what makes the clock a non-linear system. So basically these are non-linear oscillators driven by external work, and they approach a non-equilibrium steady state. And the steady state in the case of a clock is called a limit cycle, which is a one-dimensional attractor. Sometimes these are called self-sustained oscillations or relaxation oscillations. Typically they occur when there's a bifurcation of a fixed point through a Hopf bifurcation. So let me just give a quick sketch of how this works. And I'm going to treat the wheel and anchor mechanism in a kind of adiabatic way by simply including a function which I'll call the kick function. So x is the angular deviation of the clock from the vertical, and y is its angular momentum. The first two terms on the right-hand side of each of these equations are just a simple harmonic oscillator. Then there's a damping term at rate gamma. Then there's this mechanism which kicks the clock, and I'll have a bit more to say about this in a minute. And then ultimately, of course, we need to include fluctuating forces, because the fluctuation dissipation theorem, you cannot have damping without fluctuations, or the system won't reach thermal equilibrium. Whoops. Now I've just got to go back. Here's the expression for the kick function. I could include the anchor and wheel mechanism in the equations of motion, but then I have 4 equations of motion, and it's all very complicated. But typically the anchor and wheel reacts very quickly and relaxes to a steady state, and can just simply be described by this kick function, which, as you see, is a nonlinear function of the position and momentum of the pendulum. That's mu is the size of the kicks. That's the sine function, which just, so this thing just takes the value plus or minus 1. And sine naught is just something that depends on the design of the clock and how it's being set up. So you can solve those equations in the long time limit, and you see that it will settle onto this limit cycle without noise. So the square pulse there is the kick function, just turning on and off, plus 1, minus 1, plus 1, minus 1. And that entrains this, in this case, pretty harmonic oscillation for the clock. So the thing I want to stress is that these are attractors. These are stable dissipative steady states of sustained oscillations due to a balance between work done by the falling mass and friction and heat dissipated, energy dissipated on the cycle. So in each cycle, work done by the drive is actually equal to the energy dissipated. That's exactly how these things form. And you can easily see that when you write down the equation of motion for the energy of the harmonic oscillator in these units. You see it decays exponentially by something that depends on the kinetic energy. Y is the momentum, so y squared is like the kinetic energy. And there's this nonlinear driving term. So the two terms on the right, the first term is energy lost due to dissipation, and the last term is work done by the clock mechanism itself. If you integrate around a limit cycle, you quickly discover that the work done exactly matches the energy dissipated over one cycle, and that's how these limit cycles form. And I stress this is in the absence of noise. So the larger the limit cycle, the bigger the radius of the oscillation is in phase space, the more power is dissipated. And this is a very important point that I need to emphasize. Large limit cycles require a large amount of energy dissipated. Large is a relative term, depends on the circumstances. Now, the simplest way to do this is to move to polar coordinates. And then you discover that the radial equation has this fairly simple form. And you can see that by setting the right-hand side to 0, you can find what the steady state radius of the oscillation is. And the angular variable just rotates. It has a slight correction due to the kick function. Remember, mu is the size of the kick. But the key point I want to emphasize is that correction gets smaller as the limit cycle gets bigger. So big limit cycles mean it's basically oscillating at the period of the pendulum, which is what you'd expect. And there's the fixed point. It's a function of both the kicking and the driving, and also the dissipation. Okay, so now we're going to include thermal noise to see what happens. I won't go through all the gory details, but just to say, we need to write down some differential equations. Technically, these are called Ito equations. And the transformation from x and y to r and theta is highly nonlinear, so one has to be a little bit careful about writing these down. But you can see that both terms pick up a diffusion term. So this dw, dw1 and dwt are just Wiener increments. These correspond just to diffusion. They have 0 mean, and their variance increases as delta t, just linearly in time. And the diffusion constant depends on the temperature and the damping. That's the fluctuation dissipation theorem coming in there. But again, what I want to emphasize is the role of the size of the limit cycle on the noise in the phase. And I'll have a lot to say about this in the rest of the talk. So you'll notice that the phase, theta, also picks up a diffusive term, but that term gets smaller and smaller the bigger and bigger the limit cycle is. So the obvious thing to do is just to assume the thing is already on the limit cycle and just evaluate the noise in the phase by setting R to a constant. And that's what I've done here. So now we see there's a slight modification to the frequency of the clock, but as the radius of the limit cycle gets big, as I've just said, that's basically the frequency of the pendulum. And there's this diffusive term called phase diffusion, which gets smaller and smaller the bigger the limit cycle is. So this is why limit cycles are very important for clock design, is that the phase diffusion is smaller, the larger the limit cycle. And that's a key in making very stable clocks. Okay, so on the limit cycle, we can evaluate the clock function. It's very simple. Sorry, not the clock function, the kick function. It's just, its size is proportional to the radius. I'll normalize that out here. And we see it's just a square function. But because the phase cos theta is diffusing, then theta t plus sine naught is a random variable. And this means the time it takes to go through 2 pi will fluctuate from one period to the next. Sometimes it'll take a little bit longer to get to 2 pi, sometimes a little bit shorter. And you can see in this simulation here, there are 3 sample trajectories. You can see the fluctuating phase quite clearly. Now, it turns out that these fluctuating periods are given by a probability distribution, which is related to something called the inverse Gaussian distribution, or the first passage time or the hitting time distribution. And here it is, not entirely intuitive, but the size of the limit cycle comes in R star. T here is not the temperature, it's the period. So that's the variable that's fluctuating. And sigma is the size of the noise coming from the phase diffusion term, proportional to temperature. The mean and variance of this distribution are here. This is perhaps the key point. The variance is 2 pi and omega, where omega is the natural period of the pendulum. I chose in the simulations to set this to 1. And the variance has this really interesting feature. By the way, these are all dimensionless units that I'm using here, so it's a bit difficult to read off the dimension. But the key point is the variance goes to 0, both as the noise, sigma, goes to 0, and as the radius of the limit cycle becomes very big. So the bigger the limit cycle, the better the clock. And the key point here, which is also true for quantum clocks, it was emphasized in this lovely paper from 2017 by Erker et al. From Hopf's group, Indiana, show that good clocks are necessarily highly dissipative. So here's a picture of that distribution, characterized by a parameter lambda, which gets bigger the smaller the noise gets. And you see it starts out fairly broad. In this example, where omega equals 1, the period is 2 pi, and it gets sharper and sharper on 2 pi as the period increases. keep an eye on the time here. Okay, so that was all classical, emphasizing that a clock is the result of the formation of a limit cycle, which is a one-dimensional attractor that the system will be pulled out onto, and it's a stable attractor if you set it up right. But what happens in the quantum case? So this is what I'm really interested in now. So I'm going to choose a particular example, which is an old problem in quantum optics, which is called collective resonance fluorescence. Basically, we have a bunch of atoms confined to a very small region of space, so they all see some driving field with roughly the same phase. And this driving field is causing precession around the X polarization of the atomic dipole. And simultaneously, every atom is decaying to the ground state. And so you get this model, this collective model, where all the atoms are being driven in phase to oscillate up and down around excited state and acquire an in-phase and out-of-phase polarization, while simultaneously relaxing collectively to the ground state. So these equations for the average values just follow directly from that master equation. I mean, it's not entirely obvious how to get that, but what I've done here is factorize everything so that I'm neglecting quantum correlations in the system. Clearly the atoms are in some massive entangled state between all their individual excitations, but here I'm just factorizing everything out. And they can be solved. It turns out that there is a fixed point which is stable for small driving, which is not too far away from the ground state. But as I increase the driving field omega, increase the laser power, this undergoes a bifurcation called a Hopf bifurcation and creates a limit cycle at a critical value of the driving determined by the number of atoms and the spontaneous emission rate for each atom. Gamma is the spontaneous emission rate for each atom. So I tried to draw a picture here. It's not terribly enlightening. I've tried to draw it on this so-called block sphere. Because these things are pseudo-angular momentum, everything has to sit on the sphere. And it's way over here, just oscillating around on the sphere. Yeah, not terribly informative. But the curious thing about this problem is that many, many years ago, 1979 in fact, Puri and Lawande found an exact steady state solution to that master equation. This is very often difficult to do, but here you can just write it down. And it's given by this expansion in essentially normally ordered power series in the raising and lowering operators for this angular momentum system. J minus takes you up through all the states of this harmonic oscillator device, this rotor, and J plus takes you up and J minus brings you down. So if we have a steady state, we can easily compute the average values. And if you plot the average value of Jz, which is the collective population inversion in the system, you see as a function of the scaled driving field, it's completely smooth. There's no evidence here of a limit cycle whatsoever. Something special happens around omega equals omega naught, as we expect. Down here, there's a fixed point. Up here, there's a Hopf bifurcation, but we see no evidence of anything oscillating here. And that's because this is a steady state. It's already taken an infinite amount of time to get here. And as I'll show in a minute, there's a great deal of phase diffusion which takes place due to quantum noise on that limit cycle, which causes it to spread right around that ring on the block sphere. So you can't see a limit cycle by solving the steady state dynamics. Neither can you see it by just exactly solving the unconditional dynamics of the master equation. Above the Hopf bifurcation, you just see Jz oscillating but slowly relaxing to its steady state. No limit cycle. And the reason for this is phase diffusion. And to see the limit cycle, you have to make a measurement. So it turns out to see it, you must make a phase-dependent measurement, which in this case is homodyne detection. So we need to detect the field radiated by the dipole in order to see that the dipole is actually oscillating. So technically, we take a little bit of the laser that's driving the atoms, put it through a phase shifter, and then mix it on a beam splitter to get some interference. This is homodyne detection. Run it onto a photodetector, and we get this noisy photocurrent coming out the end. So in all these discussions, I'm going to emphasize the key role of measurement and the kind of measurement you make in extracting your classical intuition about limit cycles. Of course, if I counted photons, I'd get a very different picture. A photon is not a phase-dependent measurement. So it's key here that we do these phase-dependent measurements. Okay, so what do you get? Well, many years ago, we worked out, and lots of people did this, Howard Carmichael initially, and others around the world, myself with my student Howard Wiseman. The key idea is to realize that while the measurement record is a classical stochastic process, a fluctuating homodyne current, that classical stochastic process is conditioned on a quantum stochastic process, which we call the stochastic Schrodinger equation, that you can't see. But every time you get a small increment in the current, that reconditions the state of the source, the quantum state, which then changes the statistics for the fluctuations in the current in the next time step. So if you like, this little dot dash line here is the boundary between the classical world up here, which is the measurement record, and the quantum world down here, which is conditioning the statistics of the measurement record. So it turns out that in this case, the classical observed current has a term which depends on some phase dependent term. So phi equals 0, this is just Jx, and that's what I'll be assuming throughout this talk. But this little c here tells you it's conditioned on the entire previous history of the current up to that time. So if you like, this is sort of weak state reduction on the fly as the system is providing information to the outside world in terms of increments in the current. And over here we see this familiar diffusive noise term, which now doesn't scale as temperature because I'm doing this all at 0 temperature, because at optical frequencies the world is indeed very cold. It just depends on the spontaneous emission rate. So here, any noise is due entirely to spontaneous emission, purely to quantum noise coming from spontaneous emission. So that's the classical side of what's going on. But to figure out what these conditional moments are, there's a somewhat terrifying equation here called the stochastic master equation. The first two terms are what we've seen. That just describes the unconditional irreversible decay of the dipole in the ensemble. But now we have this highly nonlinear term here, which is always reconditioning the state, essentially trying to project it back into something close to a pure state. So this function h is highly nonlinear. It acts on rho, but it depends on rho itself. And that nonlinearity is just telling you that the future will always be conditioned on the past and has to have a very history-dependent behavior. Well, you can write down these stochastic dynamics, equations of motion. Perhaps I won't say a lot about that. I don't want to factorize anything here because of the quantum noise is the key to driving it. But let me just plot some pictures. So here I've solved the system by literally solving the master equation in the eigenstates of Jz for 10 atoms. And the red line is what you get for a particular conditional dynamics. So you calculate Jz by solving the stochastic Schrodinger equation and calculating the conditional mean. And the blue line is the semi-classical. And you can see what's happening, that there is no decay of the oscillation. It just continues, but it is fluctuating both in phase and in amplitude. And you can see the phase diffusion that's coming in there simply by the fact that it's drifting in and out of phase with the semi-classical noise-free calculation. So the essential lesson is to see the limit cycle, you have to look for the limit cycle, that's not too surprising, by doing the right kind of measurement, and then you see the familiar picture of phase diffusion, but now the noise is entirely quantum noise and not due to temperature. So quantum noise leads to phase diffusion. And as you make this system more and more macroscopic, as the number of atoms gets bigger and bigger, not surprisingly, the phase diffusion does get smaller and smaller, and the system behaves more deterministically. So the limit cycle in this case is driven by quantum noise at 0 temperature. And I'll come back to that when I discuss machine learning. Okay. Now, let me move on to the thermodynamics of machine learning and make the connection to clocks. It may seem a little mysterious why I've been talking about clocks up to now. So we're all familiar with the marvels of machine learning, all these various incredible tools for playing games like Go or composing music in Google's Magenta or text generation in GPT-3. It's everywhere. It's hard to avoid machine learning in any branch of science these days. But what I want to talk about is the thermodynamics of machine learning. And the first thing people always ask me is, how can an algorithm have thermodynamics? That doesn't make a lot of sense. But the key point is that deep learning neural networks are, in fact, in my opinion, trying to simulate physical systems. And the whole business got started by extracting from some understanding of neurons in the brain what kind of dynamics, what kind of physical systems might do learning. But in any case, if you look at the power consumption of the training of these very large neural networks, you'll quickly realize that thermodynamics plays a terrifying role because of the cost of the energy required to train these things is unbelievable. Probably doesn't have to be that way, but that's certainly the way it's being done at the moment. Certainly the brain doesn't need gigawatts of energy to run. It runs on 100 watts, so something's missing in that picture. Now, this is going to be a bit like preaching to the converted, I guess, for many of you who are experts in machine learning, but I'll put it up anyway because I think it's useful rather than going through too many equations. So here's my simple attempt to explain a binary classifier machine learning, which I'll call the parable of the sheep and the goats. So you begin with a whole bunch of images which are either definitely sheep, which are on the left, or definitely goats, which are on the right, and at random we drop one into the machine, and it can come out either on the goat side or the sheep side. So initially, before it starts learning, it doesn't do anything. They just come out randomly on the goat side or the sheep side. But we add this feedback step where every time we get an error, we run a control mechanism back to the machine to change some parameters inside the machine to reduce the error probability. And eventually, when the whole thing has settled down on the training data, you will find the probability of error can be made very small. Never zero, for a very important reason, which is connected to thermodynamics. So before it starts training, the entropy is really large. It's basically the number of samples. So this is in thermodynamic units, kBt log 2, because I said the initial choice of images is 50-50. But obviously after training, it's much, much less than that. It's roughly n times epsilon if the probability of error epsilon is small enough. So there's been a huge reduction in entropy. And of course, that's coming from the fact that this system is externally driven and operating under feedback. So it tells you straight away that if this system was built as a physical system, which is mostly what I'll be talking about, heat and entropy must be dissipated during training. The question is how much. So here's a very simple model of a binary classifier called the perceptron. Many of you will be familiar with this. We have a bunch of inputs here, x1, x2, which are weighted by some factor, w1, w2, w3, and then summed. And this then runs into something called the activation function, but I'll call it the activation switch because I want to think about this as a physical device, which is an open, nonlinear system driven far from thermodynamic equilibrium, as I'll emphasize in a minute. It requires work to keep it running, and it dissipates heat. But anyway, eventually a binary variable comes out. Is it a sheep or is it a goat? And then we compare that with the label of whatever it was we put in. We either put in a sheep or we put in a goat, and we check to see it's come out in the right channel. And if it's come out in the wrong channel, we then send an error signal back and modify the weights. So in the simple perceptron model, we're always feeding back onto these weights. So we keep running this thing around and around and around until it settles down to a very low error probability. So this is the technical bit because I want to emphasize how the weights are changed depending on the output. So remember, X is the training data and WT, so X is a n binary variables, say, or real numbers. The weights could also be real numbers. But this activation function, and this is the key point, can only have two values. It's either 1 or 0, depending on whether this Heaviside step function has an argument which is positive or negative. If it's positive, it outputs 1. If it's negative, it outputs 0. And so the idea is if you have correctly labeled training data, you keep running the machine until the error between the correctly labeled data and the output to the device is made as small as possible. And then we change the weights a little bit depending on the difference between the two outputs. L is something called the learning rate, which I'll come back to in a minute. But the key point to realize is if this is realized as a physical system, there's a feedback based on an error signal going back and changing the weights. And the weights are in fact doing work on this device. And so therefore you're always adjusting the work being done on the system. Furthermore, the output, the binary variable, is itself a random variable because the thing makes mistakes. So this necessarily means the way the weights are changing in this physical device is also a random variable. So the feedback is an error signal. It has some stochasticity to it. And so the weights acquire some stochasticity as a result of that. Now, physically realized, this activation function is some sort of nonlinear dissipative system. An example is a double well with large friction, which is called the Smoluchowski process. So over here, we have a double well with a particle biased on the left, and then we can turn on a strong constant force, a linear potential, to drive it to the right. I say it's always acting with large friction, so it doesn't start oscillating wildly in this thing. It always settles down and you just gradually move it until eventually thermal fluctuations will take you over into the other well. The amount of a bias you need to apply, of course, is a random variable because it will jump from one side to the other at some random time. And the stationary probability distributions keep track of which side the particle is on. So the weights control the bias in this simple example, and the noise changes the shape of the steady state response. So here I've plotted the average value of the output over many, many trials versus the bias for different levels of noise. And you can see when the noise is relatively small, we get this very sharp sigmoidal type switch, but when the noise is large, it gets smeared out. So this picture one typically sees in books for the activation function is a steady, in this example, in this physical example, is a steady state response curve. It doesn't tell you what's going to happen in any given individual system. But we can look at what happens in an individual system because the Smolachowski process can be easily simulated. And here what I've done is plot the value of y as a function of time for different levels of noise as I sweep the bias along a linear ramp from just biasing it from tilted to the left to tilted to the right. And you can see initially if there's a lot of noise, these three examples all switch very quickly from one side to the other. The fact there's a lot of noise in each steady state is just due to thermal jostling of the particle in each of the wells. But as I decrease the noise, eventually I get to the point where the switching takes longer and longer. And indeed, in this example here on the far right, two of the systems never switched in a given time t. Obviously, if I wait long enough, it'll probably switch. But now you're faced with a bit of a dilemma because you can't complete the training protocols unless the system has a chance to make a real choice as to whether it's a sheep or a goat. So there's going to be a trade-off between the learning rate and the level of noise in this system. So let me emphasize again, we have to make a distinction between what happens for a single realization, which are these stochastic pictures, from what happens in the steady state response in these systems. So you can see why these are getting smoothed out. If I take a whole bunch of these and average over many trials, you're going to see you get this sigmoidal function, which is the average value of y is not binary, while the actual realizations of y are pretty close to binary. So when the noise is large, the output switches quickly. And when the noise is small, the output switches slowly. And in that case I've given there, two of them didn't switch at all. So that will lead to an even higher error rate. Obviously, if I turn off the noise completely, it'll never switch. So noise plays an absolutely critical role in the physical realization of this perceptron. It's what is causing the system to switch at all. So you might think, oh, let's just get rid of the noise, but that would be a really bad idea. The system will get stuck in local minima and never go anywhere. So in the limit of no noise, there's no switching and no learning is possible. So dissipation and noise are essential for efficient learning machines, just as they are for clocks. Okay, so let me emphasize again that I'm here talking about a physical device, some physical perceptron. But those of you who are familiar with machine learning will know that there are all sorts of tricks that are used to implement the kind of feedback we need in the simulation of a neural node like a perceptron. And people have reduced the friction essentially in the way I'm thinking about it by adding in momentum terms, which helps the system find a new state a little bit more quickly. There's all sorts of tricks for adding in noise by hand. And after you look at all, and of course the feedback mechanism is nothing like what I've just described. In a deep neural net, it's based on back propagation. But however it's done, physically you are going to change the parameters that are biasing the machine one way or the other. So while it's difficult to talk about the thermodynamics of an algorithm, if you think about the algorithm as trying to model a physical system which is driven and dissipative, you can perhaps appreciate why thermodynamics is of central concern to understanding the limits to machine learning. Now, a lot of work has been done on this in the last few years, particularly by people in the in the thermodynamic business of fluctuation theorems like Karl Jasinski and Seifert and many others. And there was this lovely paper came out in 2017 called The Thermodynamic Efficiency of Learning a Rule in a Neural Network. It's a very elegant read. But let me just quickly describe what happens. It's all binary inputs, plus or minus 1 in this case. The weights are again determined by this simple inner product of all the training data and the weights. And then we simply have an output, which is on the left or on the right of the double well, sheep or goats, whatever you like, y equals plus or minus 1. And the output is always a stochastic function of the weights, and it's chosen in this paper to be this exponential dependence on the labeling data, plus or minus 1, and the weighted sum of all the inputs. And beta in this example is 1 over kt. So this looks very much like a Boltzmann factor, as you might expect for a two-state system. But they go on to show that for binary training data with true labels, y sub t, fixed by the sign of this inner product between the training data and these inputs to the perceptron x. The goal of the learning is to adjust the weights of the network such that the label predicted by the perceptron equals a true label. In other words, that the error probability is really small. And this necessarily implies the weights obey a stochastic differential equation because they're always having noisy outputs fed back to them. But in their model, the weights also satisfy a stochastic differential equation with intrinsic noise coming from perhaps some other friction process in whatever implementation they are using. They then measure the quality of the learning by looking at the neutral information between the correct labels and the labels coming on the output of the machine. Obviously, if it's perfect, the neutral information would be 1, and if it's really lousy, it's 0, but it's always somewhere in between. But the key point in their derivation is to show that the neutral information is bounded above by thermodynamic quantities. The sum of the heat dissipated by the weights, as you're continually adjusting these potentials and dissipating energy, and the change in the Shannon entropy of the weight distribution of a single weight. But let me give a much simpler example of how we can do that for the double wells. So in the double well case, we can use something called the Crammers method just to make it a kind of binary switch from left to right. Technically, we're turning a Fokker-Planck equation into a jump process, a master equation, where it's either on the left or either on the right, and just jumps backwards and forwards. So y is 0 or 1. We can then write down a classical master equation for the probability for it to be 0 or 1. And gamma 1 is the transition rate from state 0 to state 1, and gamma 0 is the other way, 1 to 0. What do we see? Well, the output is either 0 or 1. It's always a binary variable, but it obeys this simple classical Poisson point process. So when yt is 1, the first term is 0, and the second term will be 1, unless dn minus is 0, in which case it isn't. But as long as dn minus is 1, it jumps from 0 to 1. And the probability for these jumps is given by these rates, gamma, times the time step dt. So that's all a bit technical. But the steady state distribution you can write down, and it's exactly the kind of Boltzmann factor that Galt and Seifert were using in this system. So if it's biased more towards 1 than more towards 0 than to 1, the steady state probability to be found in state 1 will be small. The input data can be a binary bit string. We let the weights of this exponential back here, epsilon, depend on an inner product of the weights and the training data, exactly like Galt and Seifert did. Then you can write down the steady state equation for the output, and it's this typical sigmoidal activation function that depends on the weighted sum over the training data. But of course, as I've tried to emphasize, that's the steady state behavior. One has to actually look at the stochastic differential equation for the observed output. And the point is these jump processes between 0 and 1 and 1 to 0 depend upon this bias, this inner product of the training data and the weights. So that means this epsilon t can be written simply as the inner product of the weights at time t times some training data. And learning is defined by giving a stochastic differential equation for the weights in the system. The cost function to be minimized is the error probability. You don't want sheeps to turn up in the goat output. So we want to try and minimize the error probability. Now, just using the chain rule, you can show that the rate of change of the error probability is given by the inner product of the change in the weights times the gradient of the error probability with respect to the weights. And so if we choose the weights to be always parallel, the change in the weights to be always parallel to the gradient, we'll get a fast convergence, and this is what is usually done. So we write down an equation for the weights, which involves this learning rate, L of t, and the gradient. And this really simple example, that the error function is just a bowl, very simple. So here's a really trivial example. I just don't put any of the details in. I just say this bias parameter epsilon is going to be a stochastic function of whether or not it comes out in the wrong channel. So basically it says, if it comes out in the right channel, do nothing. If it comes out in the wrong channel, change the weights a little bit so that epsilon changes by an amount proportional to dt. Then you can quickly write down what the average learning rate for this process is. And you can see there it's a decreasing function of time. And of course, the more dissipative it is, gamma t large, the quicker you can learn, but then the more heat and entropy you will generate. So it's a very simple way to see how feedback leads to stochasticity and learning that looks more like conventional machine learning in terms of gradient descent. Now, what I want to do next is, instead of looking at a perceptron based on something which is either 0 or 1, I want to look at a perceptron which is based on whether or not the system is on a limit cycle at the output. So this is inspired, it's just the typical model for neurons in the brain, the so-called leaky capacitor model. Let me give a quick example. Here's a biased van der Pol oscillator. It's like a harmonic oscillator with nonlinear damping, and there's some driving term A, and it has a stable limit cycle whenever the modulus of A is less than 1. So what you can do is set up the weights so that when it's going to produce the right output, a limit cycle forms and the system produces spikes and output pulses, or nothing. So the dissipated energy in this system is easily calculated. It's just the integral of the kinetic energy over a single cycle, say. And here's a picture. So what I've done here is plot the dissipated energy as a function of time when the system is either biased where there is no limit cycle, and that's this curve you can hardly see at the bottom. So it hardly dissipates any energy at all when it's just sitting down there at its fixed point at the origin. But when it's biased above the limit cycle, you see the power dissipated just keeps going up, and it goes up in steps. And the reason it goes up in steps is because it's basically a clock. So every time around a cycle, there's a bit more energy dissipated. And so the sum just keeps going up. So what this power dissipated energy is telling you is that it's basically increasing according to the ticks of a clock. And to run this thing as a perceptron, obviously we don't want to have to wait for a huge amount of energy to be dissipated. We want to operate somewhere down here for a short time. So here's what happens to the biased van der Pol oscillator. The top picture there is the momentum variable, 3 samples. You see it's highly noisy. And if I plot the energy dissipated, instead of getting a nice simple staircase, I get this thing which fluctuates around all over the place. So you can see that if I say, well, let me just sit down here and I'll say, well, a limit cycle, the perceptron is spiking after some time t when the certain amount of energy is dissipated. Obviously, this energy will get fed into something else further down the line. Perhaps I won't go into too much detail here, but the standard way to treat a Hopf bifurcation is through what's called normal form. Here's the old diffusion terms appearing once again. Sigma quantifies them. Again, changing to polar coordinates, you can see that there's a limit cycle given by r squared equals mu, the strength of the driving in this model. And the circular limit cycle is a circle in this case, and the frequency is omega. But when you include noise, of course, it will fluctuate. So what we can do is use mu as a bias term for our limit cycle. So if mu is less than 0, there is no limit cycle. If mu is greater than 0, there is a limit cycle and the system will pulse. And so we can use that as the bias parameter that we're going to feed back onto to build a perceptron. But the key point, of course, is this noise. There's always phase diffusion on the limit cycle. After all, it's a clock. And the noise gets smaller the bigger the driving. The larger mu is, the bigger the limit cycle. This gets smaller. And sigma, of course, depends on temperature in a physical problem. So here's a simple way to make a perceptron. We'll just say, we will decide that the system is pulsing after we've seen, say, 3 or 4 steps of the clock. So we set it to this Heaviside step function, just count the number of cycles we've seen. After I would say, okay, that's definitely pulsing, it's not just noise, and we'll switch the output. So you can easily extract a clock signal from this just by using a Heaviside step function of the power being dissipated in the device. Let me just give some examples. Here's the Van der Pol oscillator, where I look at the power being dissipated, and you see it spikes, and the energy being dissipated has this irregular staircase. And so depending on where I put my threshold for a limit cycle, I might say, well, it switches after 3 steps. Then that's going to take a certain amount of time on average to occur. Just like in the double well model, you have to allow a certain amount of time for the noise to drive the system to the correct state. So let's just take a really simple example where I say this is not a very good example, but just to show you what happens. 1 tick of the cycle means I've got a limit cycle. I see it go right around 1 period. And here I've plotted the error probability for the device to identify a limit cycle as a function of time. And when sigma is really small, lambda is big, and I get this blue curve. So it switches almost certainly at omega equals 2 pi. In other words, sorry, the period equals 2 pi. The frequency is 1. But as I make the noise bigger and bigger, this gets blurry and becomes more and more ambiguous whether the system is on a limit cycle or not. So this can be used exactly in the same way as the error signal for a regular old fixed point perceptron. You can easily come up with systems that do exhibit this, quantum systems. One here is a tunneling system. I guess I should emphasize, I haven't specified here whether this is thermal noise or quantum noise coming from spontaneous emission, but clearly for a quantum clock, this would be limited entirely by quantum noise. So you can build a limit cycle out of this. What happens is that the tunneling rates depends on how close it is to the barriers. And once it's basically a carbon-60 molecule jumping back, just oscillating backwards and forwards in a harmonic potential at the bottom of the Leonard-Jones potential of the forces between the gold electrodes. I won't go into any detail on that. We studied this many years ago. More recently, Jasinski has looked at the classical stochastic thermodynamics of this device. And you can easily see how you can make it a perceptron by changing the bias between the source and the drain, basically changing the coupling between the electric charge and the harmonic oscillator motion. You can write down circuits for these things. You can have a little resistor to determine what the output power will be in this device. And you can easily show how to build very complex networks of these things. So the number of electrons on the dot just oscillates between 0 and 1, but the voltage coming out of this spikes. And you can connect lots of these together to make very large arrays of a quantum nanomechanical clock perceptron, where now the noise is entirely due to quantum tunneling, not due to thermal noise at all. Obviously, you could also make it work with thermal noise. That's going to dissipate a lot more energy. But the key point is you could make this thing run entirely with quantum noise. Okay, let me come to the comments and conclusions now, and then we can take some questions. So what about this question of very low temperature? I've said, well, if we run these devices in the quantum domain where they're dominated by quantum noise, thermal noise is irrelevant. Now you might think this is somewhat paradoxical, because I said initially that you need thermal noise to get perceptrons to work, to get machine learning to work. But that's all a classical picture. The point is, as we reduce the temperature, we eventually get to the point where there is no thermal noise left. There is only quantum noise. And so the device will continue to learn fine, where the classical version of it would have long ceased to function because it will get stuck in local minima. So what about this question of low temperature? The nanomechanical system I go has to run at millikelvin temperatures, but the point is that it's a relative thing. If you operate at optical frequencies, the lab is already cold. H bar omega at optical frequencies is much bigger than KT. And of course, the occupation probabilities of the excited states thermally is exponentially suppressed. Very nice model of this by Hideo Mabuchi, based on a coherent perceptron for all optical learning. It's a very fully worked out model operating at optical frequencies, and it's based on bistability in a non-degenerate parametric oscillator. It doesn't use limit cycles. It's based on something much closer to the double well model. Of course, this brings us to the question of neuromorphic computing, which is essentially what I've been describing, but in a quantum limit, not necessarily a classical limit. And there's been a huge amount of progress in this, some of which you can see in this review paper, where they talk about spike processing, which is just another name for limit cycles. Of course, they don't necessarily last for very long. You want to turn them on and off depending on the bias in the training data. And you need to have some protocol that determines how long you let it spike for before you can be sure that it can switch anything. Now, of course, the question of quantum tunneling driving machine learning is an old one. It's basically the question of quantum annealing. So let me say a few comments about that. Quantum annealing is not usually dissipative. It tends to be based on a so-called adiabatic quantum computation, where you want to find the ground state of an interacting number of spins, and you start it off where they're not interacting with some, in this case, a bunch of spins where there's an initial field polarizing in the x direction, and you gradually ramp up the interaction so that it ends up in some highly correlated ground state, which minimizes the energy. So these are used for optimization problems. But you're trying to find a ground state. That's the whole point in these systems. So they're not usually dissipative. But in a dissipative system, and here's a review, I'm sure many of you are aware of that, the whole point is that in a dissipative system, you don't care about the ground state. You care about the steady state at zero temperature. And that can also solve an optimization problem. And this was something that Yoshi Yamamoto realized a few years ago, wrote some very nice papers on how to get bifurcations in ground states, which solve an Ising model, a classical Ising model. And recently, Sally Shrapnel, Michael Cumming, and I wrote a version of this that uses the Kerr Ising model. We were able to fully solve it at zero temperature and show the key role played by quantum fluctuations as you pass through the bifurcation to the steady state that optimizes whatever algorithm it is you're trying to optimize. Nobody has implemented this at the quantum level, although there's been various classical versions of it. So of course, what I've all been talking about here is analog machine learning. And at the moment, most machine learning is realized on digital computers, but you could build special devices, as I've said, neuromorphic devices. But the whole business of machine learning has an ancient history. In fact, it's even older than von Neumann machines and digital computing. It goes back to this early paper by Shannon on general purpose analog computing. It basically looks like a whole bunch of coupled clocks, although he didn't call them that, he called them just rotating cylinders. The question that people always ask me is, what about universality? Well, some of you may know, but it's been well established now that these analog machine learning devices are universal in the Turing sense, in that any function can be simulated by the dynamics or a map corresponding to these continuous models, even in the presence of noise. And of course, that's critical. And there's this very nice thesis from the French group, might have been this group here, I'm not sure, that discusses many of these things. And the key point of here, of course, is unlike ordinary unitary quantum computing, where noise is a bad thing, here it's a good thing. It's what helps you learn. So let me just come to my conclusions. Coupled clocks as dissipative limit cycles can form the basis of neural networks for machine learning. That's not new, that's just spiking. It's the way we expect the brain works, at least some of it does. But at low temperature, classical machine learning will fail because the thermal noise will prevent it from switching and finding new minima. But the quantum case will just work fine through spontaneous emission and tunneling. But a key point in the quantum case is that measurement noise plays a crucial role for quantum clocks. You have to measure the right thing to see the limit cycle. And so noise is now just not something that really is there. It's a critical function of what it is you actually measure to provide the feedback to this system. We can then imagine engineering novel kinds of reservoirs or baths for the system to dump its energy into, thereby controlling emission and tunneling events. And then if I really get carried away, I could speculate on what kinds of quantum learning agents or even life could be out there that operates at incredibly low temperatures or at extremely high frequencies, where everything is done through quantum tunneling and spontaneous emission rather than thermally activated chemistry. So I'll stop there. Thank you very much.
Yeah, Gerald, thank you so much for a fascinating talk, spanning from clocks to machine learning over thermodynamics. That's absolutely fascinating. I'm sure we will have some participants asking some nice questions. Ilya, do you know if already there are some questions in the pipeline?
So far, there is no questions, but if anyone wants to raise their hand and ask question, or if people now type in the question in Q&A, I'm happy to read it.
Yeah, maybe while I see there is one question coming, Ilya. I can give the okay, Anikan. Sorry, Ilya, that's your job.
Yeah, Anikan, you're welcome to talk.
Thank you very much. Thank you very much for Prof. Milburn for the excellent talk. First of all, I'm just learning how to adapt machine learning to the kind of problems that I'm interested in. So I'd like to know what your opinion is in terms of adapting this approach that you've espoused here to finding the global ground state of, let's say, an n-body quantum mechanical system. I know that you've talked about a binary kind of model that treats the perceptron as an on-off state, but do you see a scope here for using this within the context of condensed matter theory? Thank you.
Thank you for your question. That's an extremely good question. Okay, so the kinds of models where you seek a ground state to minimize some energy function, you're essentially minimizing a cost function, in this case, the energy function. They're typically optimization problems, but as you ask in your question, they could also be interesting questions in condensed matter physics. And I think there is some work done on this. Certainly in ion traps, you can set up analog simulators to find ground states of fairly complicated condensed matter systems, and then just go in and measure the state of each and every individual ion. There's been some very beautiful work done on this with XY models, biased XY models in Innsbruck, where you could even start to estimate the entanglement in the ground state between different ions. So while they're not so much machine learning algorithms, they're more in the spirit of building a device to simulate a interesting condensed matter system by using some other more easily engineered quantum system to do it. The interesting case I'm been working with recently is to use steady states rather than ground states. Now, often the steady state is a ground state. After all, everything's cooled to 0 temperature. It will be in the ground state. But in driven far from equilibrium systems, of course, the steady state's not a ground state because the system is non-thermal equilibrium. But it nonetheless can exhibit fascinating bifurcations which can be used to solve interesting optimization problems. And that's what this coherent Ising model of Yoshi Yamamoto seeks to do.
Thank you.
Okay, Thomas, you can ask your question.
Yes, hello. Hello, Gerald. This is Thomas Conrad from Durban. And thank you very much for the nice talk. I have a question concerning the picture of continuous measurement and feedback. So, I mean, if you have continuous measurement with feedback, then you can drive a system into a predetermined target state. And can you now express in this picture of continuous measurement with feedback, this machine learning process? So are you trying then to learn during the measurement what the target state is, and then you drive it into the target state by changing your feedback, or how would you formulate this in this picture?
Yeah, excellent question, extremely good question. So as you rightly point out, you could use the feedback to what it's called adaptive feedback. So you could also feedback onto the actual measurement itself. So you could, for example, change the phase of the local oscillator in homodyne detection, or you could switch from a phase-dependent measurement to photon counting. So there is a great deal of scope for investigating how the actual nature of the feedback onto the measurement itself would enable you to get to new kinds of machine learning protocols. I haven't got any examples of that. The other thing to emphasize that while in classical physics, all feedback is measurement feedback, in the quantum case, there is a uniquely quantum kind of feedback, which is irreversible, but doesn't depend on measurement. And this kind, Howard Wiseman and I called it all optical feedback some years ago. It enables you to do things with feedback in quantum mechanics that you could never do with measurement-based feedback, because the uncertainty principle would require you to add too much noise. So with coherent feedback, there's a huge amount of scope for engineering very complex kinds of feedback circuits. And Tadao Mabuchi is perhaps the leader in trying to develop these things. Certainly they can be a wonderful source of building new kinds of quantum clocks. I don't know if that answers your question, but it's probably the best I can say at the moment. But it's a very good idea to think about how to use conditional dynamics to artfully construct new kinds of learning protocols. In other words, as the information comes in, you can begin to change the kind of information you seek.
Thank you very much. That sounds very exciting. Thank you very much, Gerard.
Sure.
Okay. And before Camille can ask his question, I will read the question from the Q&A. It's asked by Khaled, and he's asking, is this thermodynamics come to evaluate the AI model that I built, or just to evaluate the validity of the AI model on the physical problem of my interest?
It could be that, but I'll tell you what my motivation is. I'm interested in what kinds of artificial devices, what kind of robotic devices could be built that could learn. And these will necessarily be limited by the physical resources that you have at your disposal. So in other work I've been doing with my colleagues at UQ, including the philosophy department, we're very interested in understanding the role of learning and intelligence in open systems. And there, the key is dissipation. And we're interested in how learning systems can acquire causal information and how that is aligned with the thermodynamic arrow of time. So they're the kinds of questions I'm interested in, which is what has led me to think about the thermodynamics of machine learning. Nonetheless, I think if you can come up with a special purpose neuromorphic artificial learning machine that doesn't require gigawatts of power to run, you would be a very popular person.
Okay, thank you. And Camille, you can ask your question and unmute yourself.
Okay, so yeah, thank you for the very interesting talk, which raises several questions, but yeah, I will just limit to one kind of general question, which is, yeah, it's more maybe than a comment. So you showed in several examples how irreversibility or noise is important for the task of learning. And so there's another, the task of information processing, which might look quite related to learning. And for this task, so there's, for instance, the quantum computation, which is famous to be unitary. So it looks like when it comes to information processing, noise is not welcome, again, because, for instance, quantum computation is designed as unitary operation. So yeah, I just wanted to know if you have any what's your views on this kind of paradox, I would say.
Yes, it is. It's an extremely good question. And obviously, the various governments around this world are spending hundreds of millions of dollars trying to build a what I would call a conventional quantum computer, it doesn't sound silly, which attempts to implement unitary processing in the face of noise. And of course, that requires very sophisticated error correction protocols. Of course, we know why these are desirable. They can solve all sorts of problems more efficiently than a classical version of the machine would. But obviously there you want to minimize the amount of dissipation. So the sorts of machines I've been talking about are somewhat different. They typically would be used in optimization problems. But I can see a clear role for a hybrid machine. So I can see a role where, for example, there's a great deal of coherence going into storing information in a quantum memory. So you could imagine a robotic device going out there with its sensors, acquiring information and storing it in a coherent fashion in a quantum memory, and then making collective measurements on the quantum memory by essentially doing a quantum computation on the quantum memory. then the output of that could run into either a conventional machine learning or a quantum machine learning. So I think ultimately the sorts of devices we will have will be hybrids. Some will be down to dissipative learning devices, but other parts will be highly coherent, conventional quantum computing. But at the moment, the objective is to solve very different kinds of problems, optimization as opposed to, say, factoring or physical simulation.
Okay, yes, thank you very much.
Okay, I don't see any more questions or any more hands. So
Okay.
I think I can hand back to Francesco.
Yeah, then Ilya, thank you very much for moderating the questions. And probably, you know, since all good talks need to last about 1 hour, it's probably the right moment to come to an end of this colloquium, and to thank Gerard very much for a fascinating talk that probably raised some interesting questions and probably potential for many new interesting research direction. So thank you very much for that, Gerard. And at the moment, I don't know if I need to wish you a good night or a good morning, because you're probably somewhere in between. Some kind
yes,
of...
it's about 1 a.m.
Yeah, some kind of...
I can't do much dark, so I'll probably just go and have a rest.
Yeah, no, that sounds like a good plan. Yeah. So Gerard, again, thank you very much. And I'm sure we will stay in touch and hear from each other very soon again. So thank you very much again for your time and for waking up in the middle of the night for giving us an excellent and very stimulating talk. So thank you very much.
Great.
Yeah.
Interesting.
Thank you very much
Bye.
to everybody. Thank you. Bye-bye. Good night. Thank you.
Thank you. Bye-bye.